Y'all can still hear me, right?
Yeah, we can still hear you.
Okay, I just started the screen recording. Okay, so because I forgot to tell everyone what happened because I did the screen recording late, basically we're just doing the initial condition first for this problem. So open the capacitor, short circuit the current, and we have IL and VC, and we're gonna try to solve for IL of 0 minus and VC of 0 minus. So this is like what you really want to do like at the very start of any of these. Find the IL 0 minus VC of 0 minus. So, VC of 0 minus here is just, so VC is the same as, because parallel across here, right? So you can just do voltage divider. So we're gonna have VC equals 12 times zero point 0.4 over 1.6. And that's gonna equal to, I got 9 volts. Oh, I mean, this is 1.2 over 1.2 over 1.6. And that's 9 volts for VC, VC of 0 minus. And then now we want to find IL, right? And IL, there's nowhere for this current to go, so IL just equals 0 amps. Good. We're done with the first part. Now we need to move on to see what it's like when t equals 0 and when t is greater than or equal to 0 at the same time. So when the switch flips after t equals 0, the voltage source will be cut off from the circuit. So I'm just going to draw it like that. And the resistor will be cut off, the resistor R1. And we can see here this is a series RLC circuit. That's this thing up here. So this is series RLC. Okay. So it says so L we have, okay, let's first, yeah, so L is 0.1, and then we still have current IL. So this is for t is greater than or equal to 0. And then the resistor R2 is 1.2 ohms, and then the capacitor is, we don't know what the capacitor value is yet. It's asking us to solve. We need to find that. We still have this. Okay, so for the conditions for t is equal to 0, we know that we can already say that VC at 0 is going to be equal to VC of 0 minus. And we can say that because the voltage doesn't change instantaneously in a capacitor. So when the switch flips, the voltage will stay the same because there hasn't been enough time for it to do anything. Okay, so we just say VC of 0 equals 0 minus, which is going to equal 9 volts. And then IL of 0, for inductors, it's the same thing, but for current. So in an inductor, current can't change instantaneously. And therefore, the current from an inductor at t equals 0 will just also be for what it is at 0 minus, and that is still 0 amps. Okay, and then something you'll notice in all the equations over here, they require for us to have so this one it's IL of t. So the equations over here are for IL of t. When you need to solve for that, you're going to look over here at these equations, right? And you'll notice that all of them ask for VL of 0. IL of 0, we already found that, right? That's this. So we already have that part. It also asks for IL infinity. Oh, and we're looking at critically damped because it says it right here. It says it's critically damped. So we can immediately know that we're going to be looking at this box here. So, yeah, and we need the VL, which is the voltage across the inductor, right? At 0. So that's and then there's a drop across inductors and capacitors, so plus and minus, right? So we need to find that, and that will be VL. Go. And the way we can find VL is we can do a KVL through the circuit. So we're going to start over here, and the current going through this whole circuit is just on IL. So we're going to have IL times 1.2, and IL of 0, we got was 0 amps. So we're going to have 0 times 1.2 plus VL. Let me check the chat if anybody thinks. Okay. Plus VL plus VC of 0, which we got to be 9 volts. And that's equal to 0. And therefore, rearranging, we can get VL of 0 equals negative 9 volts. Okay, so that's VL of 0. We don't need any more conditions for t equals 0. There's nothing else in here. We just need, looks like we just need IL of infinity. And IL of infinity, oh, let me check my notes real quick. Oh, yeah. So IL infinity, it just stays 0 amps because there's no, there's no current source or voltage source, so like it'll just stay as like what it is, like the whole thing around. Now if it was VC infinity, I'm pretty sure it'd be um 0 volts because it eventually discharges down to 0. So but IL 0 just stays at 0. IL infinity just stays at 0 amps. So we can also say IL. Okay. So that's pretty much the hard part's done, right? So that just got us pretty much everything we're gonna need in here. Other than we need C value. Yeah, we need C. Yeah, we need C because we need to be able to find alpha and W naught. So we need to be able to find this, and we need to be able to find this, and we're gonna look at R over 2L. Let me actually highlight that. Because this, remember we said this is series RLC. If it was parallel, we would use this one. Okay. So we need to find C. So we're gonna have to do a little bit of algebra here. Okay. So from C, let's see what I did. Okay, we can already find what alpha is, right? Because we have R and L. R is just the equivalent resistance, so it's got 1.2 over 2 times L, which is 0.1, and that gets us 6. And the units for that is nepers per second, NP per second. It's the same as radians per second, just like this is how like it's written in the textbook. It's pretty much the same. And then so we need alpha and we need W naught, right? But Also, if you look here, it says this is a critically damped, right? And for critically damped, it says alpha equals W naught. So we can also just say W naught equals 6. But for W naught, this is radians per second. That's just how you write it. They're the same thing, but all right. And then the so we need C still. So if we look down here, this equation, W naught equals 1 over square root of LC. We just need to solve for C because we already have W naught and L and our inductor value. So we just do square root of LC equals 1 over W naught and then square both sides. So we're going to have 1 over W naught squared equals LC. And then C equals 1 over W naught squared times L. And that gets us, when we plug in our values, we get 0.2778 farads. So that's our capacitance value. So that answers one question where it says you need to find the value of C. Okay, now what we want to do, now that we have our values R, L, and C, and we have our alpha, and we have our omega naught, we have pretty much we have everything we need to be able to construct these equations. So and it says to find ILT, so we're using this. So IL of t equals B1 plus B2t e to the negative alpha t plus IL infinity. And let's start with B1. So B1 equals IL of 0 minus IL infinity. And that's just, remember we got IL of 0 here to be 0. And we also got IL infinity to be 0. So it'll be 0 minus 0. So this is just 0 amps for B1. And then B2, we're going to use this equation here. B2 equals 1 over L, blah, blah, blah. So we're going to have 1 over L, BL of 0 plus alpha IL of 0 minus IL of infinity. So this is just gonna, when we plug our all the values in we have, so look, we got my laser pointer. So we got L was 0 0.1, VL is 0, that we got to be -9. Alpha we got to be 6. And then this IL0 is 0 and IC infinity is 0. So when we plug everything in, we have B2 equals -90 amps. So now, look, now we're just going to plug this into the equation. So we're going to plug it into this. So IL of t equals B1, 0, plus B2, -90 t, e to the negative alpha. Alpha was 6, so -6t, plus IL infinity. Remember, IL infinity we found was 0. So IL of t equals -90t e to the -6t amps. And that's our answer for this question. All good? All right. Let's do 6.17 next. Okay, this one's pretty tricky. All right. So from these two equations, we can't do what we did in the previous one because these are giving us two functions with the and there's no circuit, so we don't know what RL and C is. We're tasked with finding pretty much all the values just from these two equations. So we need to find alpha, W naught, RL, and C. So if we look at so this form with the sine and cosine, if we look at our equations over here, it's these match the underdamped, right? So therefore, when we look at underdamped, it says so. Wait, first let's factor it. Let's factor it nicely. So VC of t equals 6 e to the minus 2t minus 3 e to the minus 2t. Okay, so in the equation, we can see alpha is right here. So alpha is this. So, but if this is negative alpha, so negative alpha equals -2, meaning that alpha is equal to 2. That's our first part. Alpha is equal to 2 nepers per second. Okay. All right, and then also from this, just from this, we can see um this here, right after the cosine, the sine is WD. And we need that for to find the other stuff. So therefore WD, this is WD, and that's equal to 4, and that's radians per second. It's the damping frequency, I believe. He's like WD. Um oh right. Okay, from this, so now we have alpha and WD, and we still need to find W naught, right? So if we come down here to these equations, look for a equation that has alpha, WD, and W naught in it, right? We can use this equation here. So let me highlight that. Okay. So WD equals square root W naught squared minus alpha squared. And now we need to solve for W naught because that's that's one of our missings. So square both sides, WD squared equals W naught squared minus alpha squared. And then move the alpha to the other side, WD squared plus alpha squared equals W naught squared. Square root, both sides, W naught equals square root WD squared plus alpha squared. And now we can plug in WD and alpha into this equation. So we're going to have square root WD squared, 4 squared, plus alpha squared, which is 2, so 2 squared. And that gets us square root of 20. And that's our that's our second part. That's our W naught. So now we've already done alpha and W naught. And now we just need to find RL and C. Okay. And then to find RL and C, we're going to come back to our equations. So this, remember we said was underdamped, and we're given VC of t. See, we're not giving we're not giving IL of t, we're given IC of t. So we're gonna look at the VC of t over here. Okay. So let's see here. Okay, so look, you can tell in this equation, you can tell what VC infinity is because nothing's being added on to this in this up here. There's nothing being added on like this VC infinity. So we can say VC of infinity equals to 0. All right. And then oh, and we can also see, look, this D1 and D2 are given to us up here. D1 is 6, right? And D2 is -3. Okay. So now we can solve for what VC of 0 is, which is what somebody say something? No? Wait, are y'all talking or is my thing just frozen? I cannot tell because like with like the screen share thing.
Everyone is muted. I think it was just an echo you heard.
Oh, okay, okay. Yeah, I just get worried that like I'm not screen sharing sometimes because like I don't hear anybody talking. Am I muted this whole time? All right. Anyway, D1 equals. Okay, look, we're gonna look at this equation because this is gonna help us find this. Because in order to find D2, we need VC of 0, right? And so we need to use the D1 equation, which has VC of 0, and we already know what VC infinity is, and we already know what D1 is. So we can say D1 equal VC 0 minus VC infinity. So rearranging for VC 0, D1 plus VC of infinity equals VC of 0. And VC infinity, remember, is 0. So it's just D1 equals VC of 0. And D1 is 6, so D1 just equals to 6. Oh, wait, VC of 0 equals to 6, my bad. Okay, now we can solve for, now we can do D2, right? Because we have WD, we have alpha, we have IC of 0, and look, C is in this equation. Okay, so that's what we need to solve the algebra for. So we're gonna have D2. Okay, so we're gonna solve for D2, so we're gonna have D2 WD. I might just skip some steps so it's a little bit faster. Let's do D2 WD minus alpha VC of 0 minus VC of infinity equals 1 over C IC of 0. Oh yeah, and look, we don't know what IC of 0 is, so we have two unknowns here. Wait, hold on, I'm gonna finish solving this out. Divide by IC of 0, and then flip the equation to get C. So C equals IC of 0 all over T2 WD minus alpha VC of 0 minus VC infinity. Okay, and look. So we need to find IC of 0, right? But look, it gives us IC of T here. So when we plug T is equal to 0 for all T's in here, for IC at 0. And you just plug in your calculator, right? We're gonna get negative 0.24 amps. So now when we plug all that into here, we get C equals 0.01 farads. So that's C. That's our third part. And now what do we need to find? We need to find R and L, right? So, blah, blah, blah. And look, it says it's a series RLC circuit. So we know which of these equations we're going to be looking at, right? We're going to be looking at this. So alpha equals R over 2L. So alpha equals, so we want to rearrange for R. Oh no, we can't do this one yet because we just found C. Let's do blah, blah, blah. Oh yeah, let's do this here first. W naught equals 1 over square root of LC to find L. When you rearrange, so it's going to be square root of LC equals 1 over W naught square root 1 over W naught squared equals LC. L equals 1 over W naught squared times C. We plug in our W naught because we already have that. We plug in our C because we just got that. And this gets us 5 henries. Oh, 5 henries. And now we can do that equation over here. So alpha equals R over 2L, right? So rearrange for R. So R equals alpha times 2L. And we plug in our found values for that. And we get R equals 220 ohms. And we just found everything. See, we found alpha. Alpha equals let me box that. Alpha equals 2 nepers per second. So we found that. We found W naught over here. We found R, L, and C, and that's the end of the problem. Any questions? All right, cool. Next one. All right, 6.22. Now you have an actual circuit. Determine ICT in the circuit and plot its waveform for t greater than or equals 0. All right, so can somebody please remind me what we do as our first step here? What did I do in the first one? Never mind. Okay. We do the initial conditions. T less than 0. So t is less than 0. This is closed. So we're going to have boom, boom. Boom. Nope, I want to make that a short. All right, now we need to find VC of 0 and IL 0. VC of 0 minus, yeah. Look, there's no, this is blocking this off from the rest of the circuit, it's short-circuiting it, so therefore there's no voltage drop. So VC of 0 minus equals 0. IL, it's going to take all of this current, it's going to go all the way through here. So you have a short circuit, and if you're doing source transformation, you see it's um, going 6 amps through here. So IL 0 minus equals 6 amps. That's our first part. Now we want to do T is greater than or equals 0. Alright, so now the switch is gonna be flipped, the voltage source is gonna be cut off from the rest of the circuit, and we have a series RLC. Boom. 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 Yeah, yeah. Alright. So this is gonna be 2, which is 2, and this is gonna be IL, voltage drop VL 8. I see. This is 0.1. So the good thing about this one is we're given all of our RL and C. So that's really that really helps our it really makes the problem easier. Okay, so VC of 0 equals VC 0 minus because voltage doesn't change instantaneously with the capacitor. So we're going to have 0 volts. And IL 0, same thing. All right. And then look, now it's asking for IC of T. And we get, so that's the current for the capacitor. And we're going to get to that by taking the derivative, because you know the equation um, IC equals C dVC over dt. So we need to take the derivative of VC of t. So we need to find VC of t first. Okay. And also, we are not given what response it is for this. So we don't know if it's overdamped, critically damped, or underdamped. So we have to find that out. But we're going to be using one of the VC of t's equations. So that's VC of 0, IL 0. Let me just screenshot that. Oh yeah, we don't know which thumb that is yet. Okay. Let's just be safe and find. Oh yeah, okay. Sorry. So what we want to do if we don't know which response it is you do these equations down here, right? So we need to compare alpha and W naught and see if they're equal, or if alpha is less than W naught, or if alpha is greater than W naught. So we're given RL and C, so we can just use these. So look, let's find alpha with a series RLC first. So alpha equals R over 2L. R is 8 over 2 times 2. So it's going to be 2 neppers. And then W naught equals 1 over square root of LC. And when we plug that in, it's 2.24. Radians. Okay. Now we want to compare these two, okay? So look, W naught is greater than alpha. So alpha is less than W naught. And we want to look at which of these equations that's true for. And that is true for this. So we're going to be using this underdamped box here. All right. So, okay, so it's showing that we're gonna need VC of 0. Wait, let me just use a highlighter on that shit. We need VC of 0. We already found that. VC infinity, we need that. And we need IC of 0. Okay. So, VC of 0 was 0. Let's find IC of 0. And you'll notice that the current IL of 0 is going in the opposite direction of IC of 0. So IC of 0 is just it's just the opposite of IL of 0. It's going to be negative 6 amps. Cool. All right, and we need VC of infinity. And it's going to discharge down to 0 volts. Well, it wasn't going to have any voltage originally, so it doesn't really matter. 0 volts. Okay, so that's all of our things that we need. So now let's look at the equation. So, excuse me, VC T equals e to the negative alpha T d1 cosine WDT. Oh yeah, we're gonna need WD as well, huh? Plus d2 sine WDT plus VC. Sorry, it's going into the page a bit. All right, we need WD, right? So WD, and in order for that, we need W naught squared and alpha squared. We found that over here. So WD equals square root. So we're gonna use this equation. So square root of W naught squared minus alpha squared. And when we plug in these values up here, we get WD to equal 1 radians per second. Nice, easy number. Okay, so now we need to find D1 and D2. So we're going to look down here. VC of 0. D1 equals VC of 0 minus VC of infinity. That's going to equal, so we come down here, VC of 0 is 0, VC of infinity is 0, so that's just going to be 0. D2 equals 1 over C IC of 0 plus alpha VC 0 minus VC infinity over WD. So when we plug in all our values, because we have C, we have IC of 0, IC of 0 is negative 6, alpha was, we got over there, I think it was just 2, and then, so the alpha is just going to get canceled out by the 0, and then divide by WD. You end up getting D2 equals negative 60. Okay. And now we want to plug all those in. So we got VC T equals B1, I mean D1, wait, no, I mean E to the negative alpha T. Yeah, alpha was 2 times D1, 0 cos of WDT, so that's just going to be 1 times T plus D2, negative 60 sine of T plus VC infinity. That was just 0, so we're not going to add that on. So VC of T equals negative 60 sine t e to the minus 2t. And so it tasks us with finding IC at t. So now we're going to do that thing from before, where this over here. Okay. So we're going to take capacitance times the derivative. So we're going to take 0.01. So when we do the derivative, so let's do the derivative first and then multiply it on. So it's VC prime equals product rule I don't know how to plug into my calculator yet, so I'm just doing this. So this here is IC. But no, it's not IC yet because we need to multiply this 0.01. So now IC we end up getting 12e to the negative 2t sine of t minus 6 e to the minus 2t cosine of t amps. And that's the answer. Any questions about that one? Looks like we're good. All right. Next one. All right. Choose the value of the inductor in the circuit so that VC exhibits a critically damped response. So we know it's critically damped, right? So we know, and it says determine VC at t. So we already know off the bat we're going to be using this box here because it's VC at t. All right. So let's start with our initial conditions again. For t is less than 0, the switch is right here. So short the inductor. Yes, it's being recorded. Yep. Okay, for t is less than 0. Yeah, we're still doing this. Got an open circuit here. Could somebody type if I'm making sense? I just want to make sure. 0.1. This is IL. Okay, thank you. This is 0.004 amps. This is 0.1. So we need to find IL 0 minus and VC 0 minus. So if we look here, IL is the current coming from this to here, right? Short circuit current. So we can do a current divider. So we can do 0.004 times 0.1 over 0.2. That's going to equal 0.002 amps. Okay, for IL 0 minus. And then VC 0 minus, if we, I just visualize it better when I just do a quick little source transformation. So when we source transform, this would be 0.0004 volts. So VC is just voltage drop across this. So we can do voltage divider rule. So we're going to do 0.0004 times 0.1 over 0.2. That's going to be 0.0002 volts. All right, so that's for our initial conditions. And now we need to do our steady state t is greater than or equal to 0. So that's when the switch flips open, right? So this 1 ohm resistor will be open circuited, so we don't have to worry about that anymore. Okay. So we're gonna have that. We're gonna have that. We're gonna have an inductor. And then we're gonna have a resistor. And then we're gonna have a capacitor. Oh, and also to make it into an RLC circuit, let's do a source transformation, right? On this current source. So I'm just going to do this. So that's what does it say L is? L is, oh, we have to choose a value of the inductor for this one. Okay, so we don't know what L is, but we know C is 1 over 1.8 farads. Okay, so we got, okay. So VC at 0 here. I'm gonna put my slippers on, my feet are cold. tootsies. All right. VC of 0 is just going to be the same as VC of 0 minus because again the voltage does not change instantaneously in a capacitor. So this is going to be 0.0002 volts, and IL 0 equals, again, current does not change instantaneously in inductor, so the current is 0.002 amps at t equals 0. Okay, and all right, it's asking us VC of t. And what does this say? Critically damped. Okay, so VC of t. We need IC of 0. IC of 0. So IC, remember, if you look up here, it just shows what our IC is. Some positive and negative. Okay, look, IC. See, IL is the same current going through this whole circuit because everything's in series. So IC is just going to be equal to IL at t equals 0. So this is also 0.002. All right. And then what else do we need? We need VC of infinity is the last thing we need. So this is open, obviously, for steady state for t to infinity. So so the thing you do with voltage sources, okay, if there's a voltage, because like in the previous ones we've been doing, there hasn't been a voltage source. There hasn't been a voltage source connected to it in this after the switch flips. So when there's a voltage source connected, VC will just up well it will charge and like this is my understanding of it, it'll charge until it gets to 0.0004 volts and then it will stop. So the maximum it can get to up to infinity, so just forever, is it just charges up to 0.0004. Oops, that's a Z number 0 there. Boom. All right. And now we also need WD. Okay. And WD. Reset. So we have our R. Oh yeah, let me write R is just these two in series. So we can find which one can we find right now? Okay, so yeah, we gotta do a little bit of algebra for this. So we know it's critically damped. So alpha equals W naught, right? So alpha equals R over 2L. We don't know what L is. Okay. And W naught equals 1 over square root LC. So because alpha equals W naught, we can equal these two together. So alpha is R over 2L, and W naught is 1 over square root LC. And then now we know what R and C are, we just need to solve for L, okay? So we would have square root LC equals 2L over R. Square both sides, you'll have 4L squared over R squared equals LC. And then divide by L. Oh, my bad. We need to divide by c. So we're gonna have 4l squared over r squared c equals L. And now we need to divide by L squared. So 4 over R, oops, R squared C equals L over L squared. So now we have 4 over R squared C equals, so this is the same as 1 over L, right? So L equals R squared C over 4. And we know what R is, we know what C is. So L, when we plug our values in, we get 0.0534 henries. So that answers what our L value is. Let me see if the right question so far. Oh. Since we were given a source, would the voltage not be the same as the source? What voltage? Like at what time? Or did I already answer it? Okay, good. Yes, it's because well, look, in this just to get just we need an RLCC, one resistor, one inductor, and one capacitor. So you just add the two resistors and you just get a simplified resistance. Is that all right? Does that answer your question, David? Okay. Cool, 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 cool. Okay, so now we have our L value. We can use now we can find wait, what do we still need to find? Oh yeah, now we can find alpha and W naught. So we use alpha equals R over 2L, and that's gonna be R is we got is 0.62, so 0.1 plus 0.52, like I said, 0.62 over 2 times 0.0534 from our inductance. Alpha equals 5.8 nepers per second. And then W naught equals 1 over square root LC. And that's, so we have L, we have C. We just need to put in the calculator and we get 5.8. So look, this makes sense, right? Because it says critically damped. And we get W naught is equal to alpha. See? So that just proves it. So you would actually really, you only have to solve for one of these, but this just shows like how it proves that this is in fact critically damped. So yeah, because it already shows it here. So you could, so like, okay, now that I got alpha, I just know W naught's already this without plugging in the calculator. All right, now we can do this equation. So VC equals B1 plus B2 T e the negative alpha T plus BC of infinity. Yeah. And then B1 says equals VC of 0 minus VC of infinity. VC of 0, we remember we see here we got 0.0002 down here. Okay. B2 equals 1 over C IC of 0 plus alpha times VC of 0 minus VC infinity. And we already got IC of 0, right? Over here, remember? 0 0.002. We have alpha up here, 5.8. We have VC 0 minus VC infinity. We got here 0 0.0002. And we have the capacitance. So when we plug this all in the calculator, we get B2 equals 0 0.00244 volts. So now we can plug this all in to VC of t. So we got VC of t equals B1 0 0.0002 plus B2, right? Look at my notes. Oh, VC was oh, it's VC of 0 minus VC infinity, my bad, is 0 0.0002 minus 0 0.0004. So this is negative B1. So sorry about that. All right, so this would be negative 0 0.0002 plus B2 plus 0 0.00244, right? T e to the negative alpha t, so alpha was negative 5.8. Plus VC infinity, which is plus 0 0.0004 volts. And then when we make this look a little bit neater and we change to millivolts, we get 0.4 plus 2.44 T minus 0.2 e to the negative 5.8 T millivolts. And that's the answer for this question. All good? Let me check the questions. All right, looks like y'all are good. Okay, now I have one more. I just have this last one lined up, and I didn't go over any from the homework, so I'll just after this one, probably have to let Jimmy know. We can try going through the other ones for the rest of the time. What do you want to do? Because I won't be like fully prepared for the other ones. So do you want me to like go through them anyway, or just stop after this question? Because I can just tell Jimmy to go through them in his. Because he's got a study session later at, I believe, 6. I don't know. It's one time. So yeah, maybe just this one more problem because there are many people in here. Is that cool, y'all? Yeah, no problem. Have I helped y'all? We'll just do this one more problem. Okay, good. Waiting on what David's about to say, and then I'll do the problem. All right. Okay. Table 6.1. If you go to the textbook, right? Okay, actually, yeah, let me put in the chat. This is also, just so you know, this is on page 358 of the textbook, but I'll send it into the chat. There you go. We do get this table. We do get this table and that other table, Christian, for the exam. So you can have both. That's what she said. That's what Dr. Deepa said. Yep. All right, last one. So after this one, will pretty much be half the homework. So that's pretty cool. All right. So now choose the value of C. So we're gonna try to find C and critically damped. Okay. So critically damped, we're gonna be looking at this equation. So it says VC of T. So this is pretty much the same thing as the previous one, just this time we need to find C instead of L. All right. So we're gonna find T is less than 0, the initial conditions. So that's when the switch isn't flipped up, so everything is still in the circuit. And short the inductor, open circuit the capacitor. All right. Okay, so let's find VC of 0 minus. So for VC, right, we can do a node voltage to find what VC is. Okay. So VC, so put the ground here. VC minus 18. I'm not gonna put units because y'all know how to do that shit. Over 6 plus VC minus 12 over 6 equals 0. And then look, from this, so from this we'll get VC, and we can also find IL. Because IL is just VC minus 12 volts over 6. Okay. And from that, we get VC of 0 minus equals 15. And IL of 0 minus is 0.5 amps. Okay, cool. Those are our initial conditions. Now T is greater than or equal to 0. Now the switch flips up, so the 18 volt voltage source and the 6 ohm resistor are going to we're going to ignore that, and we'll have this the right side of the circuit. So we'll have that that voltage source, that capacitor. Volts. All right. So then from this, we're going to find, so we know VC of 0 equals VC of 0 minus because the voltage doesn't change instantaneously. So VC of 0 equals 15 volts. And IL 0 equals, again, for the inductor, current doesn't change instantaneously through an inductor. So this is 0.5 amps. Okay. And now, so this is IC. Yeah. Okay. Now we want, because we're dealing with the DC, right? We want VCT, so we need IC of 0. That's this. So IC of 0 equals oh yeah, and IL was coming down. Somebody say something? No. Okay. So IC of 0. So IL is going in the opposite direction of IC, right? So because the current is still for IL at this time, they're going opposite directions. So IC of 0 is negative 0.5 amps. Okay. And it says, it gives us that it's critically damp, remember? Oh, yeah, and then we need to also, remember, we need VC of infinity. That's also part of the equation. So VC of infinity. Remember, it charges up to 12 volts. So VC infinity is just going to be 12 volts. Cool. Oh, right. And now we need to find our C value. So from that, so we have R and we have L, so we can find alpha for a series RLC. Alpha equals R over 2L, which is going to equal, so R is 6 plus 6, 12, just to put more resistance. 12 over 2 times the inductance, and that gets us 60 nepers per second. Okay. And because it's critically damped, we don't, we know that alpha equals W naught, remember? It says it up here, alpha equals W naught. So therefore W naught is just the same as alpha, it's going to be 60 radians per second. Okay, and then from this, so remember we still need to find our C, so let's use this equation here. Oh, that's a pencil. Let's pull it up later. So W naught equals 1 over square root of LC. I want to solve for C, so we got square root of LC equals 1 over W naught. Square both sides. So C equals 1 over W naught squared times L, and we just plug in because we know those values. So C we get to be 0.02 0.0027778 farads. Yeah. So that's our C value. So that answers one part of it. It's nasty. Okay. Now we can just do the equation, right? So we have the VC of t equals B1 plus B2 t e to the negative alpha t plus VC of infinity. So B1 equals VC of 0 minus VC of infinity. We come back over here, we need to go back to see what our VC of 0 was. VC of 0, we got 15 volts here, and VC of infinity, we got 12 volts. So we're going to do 15 minus 12, so B1 equals 3 volts. And then B2 equals 1 over C, IC of 0, plus alpha, VC of 0, minus VC of infinity. Okay, so now we're going to plug in our values. We have everything. We have everything we need. We have capacitance. We got this 0.002778, and it was necessary to find the capacitance to be able to do this. And then IC of 0 got down here, negative 0.5. If my mouse will work. Okay, thank you. And then we have alpha, we had 60, and then 0 minus the VC 0 minus VC infinity, we have all that. So when we plug all that in, we have B2 is equal to 0. Okay. And now we want to put that all that into our VCT. So VCT equals B1. Oop, that's nasty. Equals 3 plus 0t, so 3 plus 0. E to the negative alpha t. Alpha was 60. E to the negative 60t. And then plus VC of infinity. VC of infinity, come back over here, it's 12 volts. So VC of t equals 3 e to the negative 60t plus 12 volts. And that's the answer. All good. Oh, hey, Worship. Worship, could you also tell Jimmy I just did the first 5 problems and I did record it, so he doesn't have to do the first 5.
Yeah, sure.
All right, thanks.
How many problems are left?
I just did 1, 4 problems.
Like 10 problems.
Okay,
Problems
gotcha.
left. So 6.32. So everything after 6.29.
All right.